How are you all doing today?
Doing well.
Doing well.
I have not yet had an opportunity to do any sort of statistical analysis of the exam or anything like that. And what I mean is that typically speaking, I go through and I see what the percent of correct answers is for any given problem, or actually for every given problem. And if that percentage falls below roughly 30%, then I will rework the problem and make sure that the correct answer was available. If it was available, I don't do anything. And if it was not available, then I usually wind up just giving full credit to everyone for those particular problems where that happens. Usually doesn't happen as more than, say, 1 or 2 problems per test, if that many. I have had a couple where no mistakes were found, and I've had a few that were outliers where 4 mistakes were found. So I haven't done that yet, so I don't know if any of your grades are going to be shifted or anything like that. I haven't even looked to see what the class average is or anything at this point. So I just wanted to let you know where I was at. So for the time being, whatever grade Moodle says you has is your grade, and that may change after I do some looking at things. I will never change your grade to be worse than what the computer tells you got, though, so I want to be clear on that. All right, so today and tomorrow we will be covering capacitors and inductors, and these are our first energy storage elements in circuits, because resistors are incapable of storing any energy. All they can do is convert electrical energy to heat. Resistors and capacitors, however, can be used as effectively temporary energy sources, but they have to be charged in order for that to happen. For these first 2 lectures, we're just going to talk about the generic properties of capacitors and inductors, but starting with lecture 13, which is on Friday, and then continuing through 14 and 15, the following Monday and Tuesday, we will actually be looking at the energy transfer relationships and how they apply to circuit analysis techniques. So before we jump into the in-class assignment regarding inductors, did anybody have any questions about the lecture material?
Yeah, I have a question. Sorry if this is a little early, but it's about the third exam. Can I confirm that it's not cumulative?
I believe the results of the polls on both sections overwhelmingly chose to have the exam be not cumulative.
Okay, thank you.
Mm-hmm. Any other questions regarding, I guess, anything right now?
Are you going to end up posting the solutions for exam 1?
No, probably if I do post them, it will be for a class in the future. If you have questions regarding any specific problems, you can email me and I will happily go over those with you, but I'm not going to generally do it just in case I wind up having to reuse some of these questions, just because things seem like they're going to be awfully hectic in the fall.
Okay, thank you.
Yep. Any other questions? All right, well, let's jump into the in-class assignment then. All right. So this first problem is with regards to an inductor. Actually, this whole set is inductor specific. We're told a 25 millihenry inductor is carrying a specific current, and we are asked to determine the voltage drop over the inductor at a specific time, the power being delivered to the inductor at a specific time, and the energy stored by the inductor at a specific time. And there's really only a couple of different approaches that we could take on some of these parts. So let's just kind of dive right in. So for part A, to determine the voltage drop over an inductor, given the current, we're just going to have to use the specific current voltage relationship for an inductor that says the voltage drop over an inductor, VL, as a function of time, will be equal to the inductor value L multiplied by the derivative of the inductor current as a function of time. So in this case, L is 25 millihenries. And then the derivative of IL with respect to time. Sorry, my wife was texting me. So let's see, we're going to have 8 milliamps minus 8e to the minus 40t milliamps. So the derivative of the constant term is going to go to 0. So really looking at the derivative of negative 8e to the minus 40t. So let me write that up here real quick. How would we perform that indicated derivative?
I distributed, oh, well, you already distributed that, sorry. It's just exponential, you bring down that negative 40 and then everything else stays the same.
All right, so we're going to have a negative 40, and it's going to have units of per seconds. And then we have a negative 8 milliamps. And then we'll have an e to the minus 40t. So if we followed the units on this guy, a millihenry is a volt, actually it's a millivolt second per ampere. So millivolt seconds per ampere is going to cancel everything out, and we're going to be left with volts. So let me do this in my calculator real quick. So 25 times 10 to the minus 3 times negative 40 times negative 8 times 10 to the minus 3 is 0.008. So that would be 8 e to the minus 40t millivolts, if I've done my math correctly, and I believe I have. If we evaluate this at t is equal to 60 milliseconds, what we're going to get is times e to the minus 40 times, let's see, 0.06. So at t, or let me move this. Seven to 5.744 microvolt. Alrighty, so that matches the answer that we get here, so that seems reasonable. For part B, we are asked to determine the power being delivered to the inductor at t is equal to 50 milliseconds. So how could we go about doing that?
The formula for power is the inductance times the current at that specified time times the derivative of the current at the specified time.
So you're not wrong. There's two ways that we can approach this. We have a mathematical expression for the voltage drop already, right? It's right here.
Oh yeah, so it would be much easier to just multiply that voltage times that current.
Well, so that's one route. We could multiply this given voltage times this current and get a mathematical formula. Or we could do effectively what you suggested, which was evaluate this current at the specific time, evaluate this voltage at that specific time, and then multiply those two numbers together. Either way is perfectly reasonable, but what I wouldn't do is go ahead and recompute the derivative because we've already done that work effectively. So that's why I kind of shied away from what you had suggested slightly. So which of those two routes do you guys want to do? Do you want to multiply the functions and then evaluate it, or evaluate the voltage and current and then multiply?
Can we do the latter of the two?
Okay, so that's evaluating the two functions. Sure. So let's start with IL of 50 milliseconds, which will be 0.05 seconds. So that is going to be 8 times 1 minus e to the minus 40 times 0.05, close parentheses, milliamps. So let's throw that in my calculator real quick. I got 6.9173 milliamps. Let me double check that I've got everything in here correctly. 8 times 1 minus e to the minus 40, 0.05. Okay, so that seems okay. VL at 0.05 seconds is going to be 8 times e to the minus 40, 0.05 millivolts. One 0.083 millivolts. And from this, our power, PL, at 0.05 seconds is going to be IL at 0.05 seconds multiplied by VL at that same time, and we get 7.489, and the milliamp times a millivolt gives me a microwatt. And so that matches there. Alrighty, for part C, we have the same basic, not really conundrum, but the same basic options. We're trying to find the energy absorbed by the inductor. The energy absorbed by an inductor, WL, is a function of time, is 1/2 L times the current flowing through the inductor squared. So our options are to multiply to square the function and then evaluate it, or to evaluate the current and then square that. So which route would you prefer to go this time?
Probably evaluate it.
Squared.
So evaluate the current. Okay. So IL of what time are we looking at? 40 milliseconds. Is going to be 8 times 1 minus e to the minus 40 times 0.04. .385 milliamps. So from this, WL at 40 milliseconds is going to be 1/2 times 25 millihenries times 6.385 milliamps squared. All right, so 0.5 times 25 times 10 to the minus 3 times the variable I stored as x squared. I get 509.575 nano. That does not look like an N. Joules. And that's exactly what we got. All right, so hopefully that was pretty straightforward, just direct application of the different expressions that I derived in the lecture for voltage, power, and energy. If there's no questions on that problem, let's move on to problem 2. So here we are asked to determine the current that is passing through a 24, we're told the current that's passing through a 24 millihenry inductor is shown in the graph. And we want to determine the voltage drop over the inductor at a specific time, the power absorbed by the inductor at a specific time, and the energy stored by the inductor at a specific time. So let's see, for the voltage, we want the voltage drop over the inductor at t is equal to 0.25 seconds. So that would be right here where I'm drawing this vertical line. So how would I go about determining that? What's my equation for voltage drop over an inductor for a given current? Let's start there. We literally used it 3 minutes
It's
ago.
the inductance times the derivative of or DIL over dt.
Yep, inductance times the derivative of the current. So how are we going to determine the derivative of the current from this graph?
Well, the derivative is a formula for the rate of change at a particular point. So we could just use the slope of that point, or the slope at that point.
Yep, exactly right. So we're just going to look at the slope. So we have a 24 millihenry inductor. And now let's get our slope. Well, we can see over the time interval from 0 to 0.3 seconds, we have a rise of 4 amps. So the right-hand side is 4 amps minus 0 amps divided by 0.3 seconds minus 0.0 seconds. So I'm looking at this point and this point and determining the slope of that line. I'm using the y2 minus y1 over x2 minus x1 method that I learned in high school. So from this, we're going to have 24 times 10 to the minus 3 times 4 divided by 0.3. So I get 0.32 volts, which is the same as 320 millivolts. So that seems easy enough. For the power, we're looking for the power at t is equal to 0.5 seconds. So at t is equal to 0.5 seconds, looking right here, or I'm trying to, but my pen is being. So let me ask you guys a question. Do I need to bother calculating the voltage at over the inductor at this point? At this specific point, let me.
No.
Would it be 0?
It will be 0. Why?
Because the current is 0.
Right, and so the current is always simply the product of the power and, the power is the product of current and voltage. So if the current is 0, it doesn't matter what the voltage is, the power must be 0. So we can see that it is 0 watts by inspection. We don't even need to do any real work. All right, for part C, we want the energy stored by the inductor at T is equal to 0.75 seconds. So that is occurring here. So how are we going to determine our energy?
Is it 1/2 times the inductance times the current squared?
Exactly right. So 1/2 times our inductance, which is 24 millihenry. So what's our current?
-2 amps.
-2 amps. Just making sure you guys can read a graph. And there we go. 0.5 times 24 times 10 to the minus 3 times -2 squared. So that's giving me 48 millijoules. 0.048 joules. All right, that one's pretty straightforward. On your exam, you should absolutely expect a problem with a graph like this that you will need to interpret to determine voltage and or power and or energy for either an inductor or a capacitor. So I put this problem in the in-class assignment because it is extraordinarily representative of somewhere between 6 and 9 points on your next test. Alrighty, and then this guy, this one's going to be a little bit of a doozy, but it'll be okay. It says, for the inductive network shown below, the equivalent inductance seen between the terminals is 6 millihenries. And it asks us to determine the value of the unknown inductance, L. So I'm going to identify my nodes. And I usually get just a ton of problems, or excuse me, a ton of questions about how to solve this particular problem in a live classroom setting. So I might just take the wheel pretty much and then ask you guys questions throughout.
For this one, could we combine them all like because they behave like resistors, generally, could we just combine them all and then leave the unknown one? And once we have like that one combined one and then that other one, set that equal to the 6 millihenries that it gives us?
We are effectively going to be doing that. There are some simplifications that we can observe as well. So I'm going to call this C, D, E. This guy is D. This guy is F. All these are F. All right, so bear with me just a moment. So between A and C, we have a 1 millihenry inductor. And then we have lots of different paths. So let's just establish one right off the bat. From C to D. No, actually, let's go from C to F. So I'm going to put F over here. And then here is B. And that's a 3 millihenry inductor. So taking care of this guy and this guy. From C to F, I have that 4 millihenry inductor. Which takes care of this guy. And then from C to D, I have a 2 millihenry inductor. This guy D. Now, from D to F, I have L, 18, and 9 all in parallel. So that takes care of this guy, and this guy. So now I have from D to E is 8, and from E to F is 4. All right, so hopefully we can see that there are several simplifications that we could make here. So somebody tell me what some things that we could do are.
We can do the bottom 3 parallels. We can combine those 3, the 18, the 9, the 18, the 9, and the 8 plus 4, 12.
Okay, so you're saying combine this guy and this guy in series and then put them
Yes.
in parallel with the 18 and the 9. Okay,
Yes.
so that would look like 1 over 12 plus 1 over 9 plus 1 over 18 to the minus 1 looks like 4 millihenries. So I'm going to erase all this stuff. And write it as a single 4. I'm trying to write it as a 4 millihenry inductor anyway. The pen thing is being difficult. There we go. All right. So that is a good, I guess what you would call simplification, but we're kind of, strictly speaking, we've ran out of simplifications that we could make now, at least is what it looks like. So I know that from A to B, we have an equivalent inductance of 6 millihenries, if I'm not mistaken. Let's look up here. Yes, the equivalent inductance seen between the terminals is 6 millihenries. So I would argue that that tells me that from C to F, let's call this LEQ 2.
It's 2 millihenries.
Yeah, 2 millihenries, exactly right. So what I'm saying is we know that this 1 millihenry inductor here is in series with this impedance seen between, or it's not impedance, inductance seen between C and F is in series with this guy here. So we can just delete out the 2 that are in series and only look at the network between C and F. Is everybody okay with that?
Yes, sir.
So if I delete this guy and I delete this guy, I know that this whole thing is supposed to look like 2 millihenries. So I have a 4 millihenry inductor up here on the top path. So if I have 4 millihenries in parallel with this guy, what does the equivalent inductance of what I've boxed in have to be?
4 millihenries.
Right, because 4 millihenries in parallel with 4 millihenries will look like 2 millihenries. So now I know that if I delete this guy, I'm looking to have just this whole thing needs to look like 4 millihenries. Right? So I have 2 millihenries in series with something that needs to look like what?
2 millihenries.
Right. So this 2 millihenries in series with another 2 millihenry inductance will look like 4, which was in parallel with the other 4, which will give us the 2 that we were looking for. So we know that this, what I'm left with, needs to look like 2. So what does L have to be?
4 millihenries.
Exactly right. So this was a exercise in combining inductances, but effectively backwards from the way that we're used to conventionally thinking about things. So we could have developed a very, very robust and ugly mathematical representation and then solved that. But I find that using, I don't want to say common sense, but our knowledge of how inductors and things like that combine made solving for this a bit more easy than just brute forcing it with math.
Isn't this technically like solving by elimination in a sense?
Yeah, in a sense, yeah.
Okay.
Yeah, I mean, again, we know how it's supposed to behave, so we're just using those rules to get rid of extra pieces of information that aren't really helpful. All right, so that is all of the in-class assignment stuff for today. So tomorrow we will be covering capacitors. It'll be a fairly similar in-class assignment. In your homework set, I believe not this one, but the next one, there might be 1 or 2 problems that involve having a capacitor and an inductor in the circuit simultaneously. Excuse me. So we may take a look at those problems specifically so that I can maybe give you some helpful suggestions as to how to approach those problems. All right. Does anybody have any questions regarding the inductor relationships that we've talked about today?
I'm good.
All righty. Well, I hope you guys have a good rest of your afternoon, and I will see you tomorrow morning.
Thank you, Dr. Hartman. See you tomorrow.